So we'll try to answer this question. Question 95. Describe the situation to which this equation refers, stating the meaning of each symbol. So when a charged particle is moving inside a magnetic field, this equation is valid. When a charged particle, first thing is this equation is valid, or this equation is used to find the force acting on a charged particle when it is moving inside a magnetic field. F is the electromagnetic force acting on the charged particle. V is the magnetic field strength. Theta is the angle between the charged particle and the magnetic field. Angle between the charged particle and magnetic field. If the angle is 90 degrees, maximum force is applied. If the angle is 0 degrees, if the charged particle is moving parallel to, if the angle is 0 degrees, if the charged particle is moving parallel to the magnetic field, force acting is 0. Okay? That's why in a motor, these two sides, there's a force acting. But those two sides, we never mark the force. Between North Pole and South Pole, have we noticed it? From small class onward, you will be doing the DC motor and the AC motor. Have you noticed the sides perpendicular to the magnetic field, we apply the force. There are two sides like that. They are parallel to the magnetic field. We don't mark the force. We'll come to that later. They can describe the situation modeled by the equation stating the meaning of the symbol P. So in a case like this, if you can straight away recognize this, that's fine. But go through the question. If you're not sure, what are you talking about? Go through the question. Go to the next part. See. You can see something there. Read that. And you see charged particles are moving in spiral-like motion. It's circular motion. Radius change is circular motion. So if a charged any particle, if it speeds up, it will spiral outward. If something speed down, slow down, it will spiral inward. So this should be circular motion. Okay, we'll go back. Okay. Now we know the particle is going in circular motion. We'll write down the equation and see. F is equal to BQV. We assume it's moving in 90 degrees. I can't see any sine theta there. Okay, maximum force is acting on the charged particle. Then I can write F is equal to M V squared over R. Centripetal force is provided by the magnetic force will equal to BQV is equal to M V squared over R. Okay. R is equal to MV divided by PQ. So as usual, that P stands for momentum. Normally in physics, simple P stands for momentum. Delta P, change in momentum. But capital P in physics usually stands for pressure. So in the description, if you can derive this, it's better. Without that also fine. So you can say when a charged particle is moving in circular motion, P is the momentum of the particle, R is the radius, V is the magnetic field, Q is the charge of the particle. They are asking stating the meaning of P only. So P is momentum. When an object is moving in circular motion, this equation is valid. If you want, you can mention 90 degrees to the magnetic field. No need. So the answer will be, they're asking what is M, what is the situation? The charged particle moving in circular motion inside the magnetic field. Then say mv is the momentum. Charged particle moving 90 degrees to the magnetic field. P is the momentum of the particle. Now we'll check this out. Particles arriving in the sun can enter the Earth's magnetic field such a way that they spiral along toward the North Pole as shown in the diagram. A spiral. Again, it's spiraling. The radius of the spiral is decreased. You see, as shown in the diagram below. As they near the North Pole, they give rise to a beautiful aurora borealis of northern lights. Aurora borealis of northern lights. You might have seen it. Then they are telling explain why the path of the particle is curved. And why the path of the particle is curved. This is very common. A charged particle moving in a magnetic field will always move in circular motion. You must be able to describe that. So this is general. This is general question and a general answer. By heart and answer. So you have to mention the charged particle is moving. First thing is perpendicular to the magnetic field. Okay. Charged particle is moving perpendicular to the magnetic field. In this case, at an angle also fine. Now in this case, charged particle is moving perpendicular to the magnetic field. Therefore, if a charged particle is moving, there's a current. There is a current. If a negative particle is moving forward, current will be backward. If a positive particle is moving forward, current will be forward. There's a current. So by Fleming's left-hand rule, the charged particle will experience a force perpendicular to the magnetic field. By Fleming's left-hand rule, charged particle will experience a force perpendicular to the motion. By Fleming's left-hand rule, charged particle will experience a force perpendicular to the motion. Therefore, it will move in a circular motion. It's a curved path. Therefore, it will move in circular motion. Therefore, the particle will move in circular motion. Okay. Now, this is a general answer. Whenever a charged particle moves inside a magnetic field, perpendicular, it will have the maximum force. Is a perpendicular to the magnetic field, like this case, charged particle move perpendicular to magnetic field. There will be a current. Again, I'll repeat, this is not for this question. If a negative charged particle is moving forward, current is backward. If a positive charged particle is moving forward, current is forward. Then we know, by Fleming's left-hand rule, the particle will experience a force perpendicular to the magnetic field. The particle will, by Fleming's left-hand rule, we know that particle will experience a force perpendicular to the motion as well as the magnetic field. But the most important thing is it will experience a force perpendicular to the motion. So when it is moving this way, force is acting this way. But the particle will bend a little bit. It's moving this way, force is acting that way. When the particle is moving this way, force is acting that way. Force is always perpendicular to motion. Now, in the electric field, this is a little different. Later, we'll talk about that. Therefore, particle will move in a circular motion. In an electric field, it will move in a parabolic path, like a projectile motion. It's a parabolic path. This is circular motion. You must be able to memorize answer for the charge particle inside the electric field and charge particle inside magnetic field. This is the answer for charge particle inside magnetic field when it is moving 90 degrees. When it is an angle, when you're doing the sum, we'll discuss that. R is equal to P over PQ. Magnetic field strength and radius are inversely proportional. Near the pole, magnetic field strength increases, therefore radius will decrease. That's one way of answering the question. But there is another way. Some set of students answer this question in another way, general way. So that way also examiner gave the marks. We'll discuss that way. Now we know, even in an accelerator, we say cyclotron, the charge particle, when it increases the speed, it will spiral outward. Decrease the speed, it will spiral inward. So that's coming from the general equation. So we'll write the general equation. BQE, magnetic force is providing the centripetal force. MB squared over R. BV cancel off. R is equal to MB over BQ. Now it's coming near to the North Pole. What will happen? It's crossing the atmosphere. It will be crossing part of the upper atmosphere. Okay? It will be crossing part of the upper atmosphere. Now there is air resistance. There are resistive forces. Now what will happen? So the particle will slow down. Now there's another point. Particle will slow down. So V is decreasing. Magnetic field is increasing. Now both will give larger denominator, a smaller numerator, either way. R is decreasing. That's another way of answering the question, not using the given equation. Again, I'll repeat. When it moves near the North Pole, it will be crossing the Earth atmosphere. Okay? So resistive forces are increasing upper atmosphere. Resistive forces are increasing. Therefore, speed will decrease. Speed decrease means again R will decrease. And again we know near the North Pole, magnetic field strength increases, again R will decrease. That's the answer. This is the perfect answer.